Welcome to Prospective Doctors MCAT Podcast, brought to you by Med School Coach. Each week, Sam breaks down the highest yield MCAT topics so you can score as high as possible on test day.
Hello and welcome to Prospective Doctors MCAT Basics with your host Sam Smith. The goal of this podcast is to cover the highest yield topics on the MCAT and provide you with some sort of insight into the questions that the MCAT really likes to ask. This podcast is going to cover redox, or reduction in oxidation, and it's broken down into two main sections. So first, I'll go into more of a conceptual understanding of what redox is, and then second, I'll go into more of a mathematical or gen chem kind of understanding of what redox is. In the first or more conceptual part of this podcast, I'm going to talk about the general definitions of, what is an oxidizing agent, what's a reducing agent, what does it mean to oxidize something, what does it mean to reduce something. I'll talk about how oxidation and reduction play a role in determining the reactivity of functional groups, as well as I'll get into a little bit of organic chemistry there of like which oxidation reduction reagents you should know and what they do. And then lastly, I'll talk about redox in biological systems, and that'll be hopefully the most interesting part of the podcast. In the second part of the podcast, I'll talk about how to determine oxidation state in like assigning oxidation numbers to certain molecules, certain atoms. And then I'll talk about the application of oxidation and reduction in electrochemical cells. And this episode is going to be a twofer because I'm going to cover topics that are on both the biochem section as well as the physics chemistry section. With that said, I hope this podcast helps, and I hope that you're staying safe and sane during these really weird times. So the first thing I want to do with this podcast is give you a conceptual understanding of what a redox reaction is and how it applies to biology and, more importantly, to the MCAT. So in general, a redox reaction is defined as a reaction that involves the transfer of electrons between two species. And in this reaction, one of the species is reduced, and the other species is oxidized, hence the name redox reaction, right? Reduction and oxidation are paired together. And a species is reduced when it gains electrons, and a species is oxidized when it loses electrons. So reduction is gain of electrons, oxidation is loss of electrons. And here we've come to really a key moment in this podcast. And I think, this is great value. You're only, 2.5 minutes into this podcast, and I'm already giving you the golden ticket, basically. And the golden ticket is this: memorize oil rig. It's a mnemonic that means oxidation is loss of electrons and reduction is gain of electrons. And I'm sure plenty of you have heard that before, but I just think that's a great mnemonic, and it's something that really does come up on the MCAT, and it is easy to mix up reduction and oxidation. So oil rig, remember that. And so a quick example of a redox reaction would be like, say I mix zinc solid with copper 2+ in an aqueous solution. Say I just drop these in. And say that I'm zinc and my buddy Jim is copper 2+. And because I'm nice, I'm zinc, I decide to give Jim copper 2+ 2 of my electrons. And so Jim readily accepts these electrons, says thank you very much. Now Jim becomes copper solid and I become zinc 2+. And in that case, I would be oxidized because I gave up 2 of my electrons, and Jim would be reduced because he took 2 of my electrons, he gained them. So that's a view of reduction and oxidation from the standpoint of the movement of electrons. And all the definitions go back to that, right? You can trace everything back to a gain and a loss of electrons. However, on the MCAT, it might not always be clear, where the electrons are moving in the reaction. And yes, you could spend the time and go through and look at the oxidation states of each atom and try to see, what is oxidized, what's reduced in a reaction. There's an easier way to go about it, though. And that's kind of like a few shorthand rules to remember that I'm going to talk about right now. And bear in mind that this really applies more to organic molecules than like metals that I was just talking about, like zinc and copper. And the shorthand rules are that reduction is a loss in the number of connections an atom has to oxygen, or a gain in the number of connections that an atom has to hydrogen, whereas oxidation is a gain in the number of connections an atom has to oxygen and a loss in the number of connections that it has to hydrogen. I think the easiest way to see this is to take something like methane, which is CH4, right? It's this molecule that has a carbon in the middle and 4 hydrogens around it. So then you go through some organic chemistry synthesis reaction and you create methyl alcohol with it, which is just CH3OH. And so what you did is you added on a OH group, a hydroxyl, group to this middle carbon. Well, how does the oxidation state of that carbon change through the reaction? Was it oxidized? Was it reduced? All you got to do is look at the number of bonds that it has to hydrogen and oxygen. Well, what happened? Well, you just gained a bond to oxygen and lost a bond to hydrogen. So just from that, I can say, okay, that middle carbon was oxidized. And so I would just remember those shorthand rules. And, if it saves you a little bit of time on the MCAT, that's great. So it should be pretty clear now as to why a redox reaction is called a redox reaction, right? You have one species getting oxidized, one species getting reduced. It's almost like redox is like, a couple's name. I don't know if anyone still does that, but I remember in high school, you'd have these couples that would make a Facebook page and the name of it would be like a combination of their names. And it was horrible, but you can see how redox is kind of similar. Like if oxidation and reduction were both dating each other, that would be their couple name. And just like one species is oxidized and one species is reduced, one of the species is the oxidizing agent and one of the species is the reducing agent. And I think this is fairly easy to remember. Take, for instance, a reactant that is getting oxidized. So what's going on? It is losing its electrons, right? Oil rig. Oxidation is loss of electrons. So it's losing its electrons. And therefore, whatever it's reacting with is being reduced. Therefore, the species that is oxidized is the reducing agent. It's what's reducing the other compound, right? Because it's like, here you go, here's my electrons, have them, I'm gonna give you these, take them from me. And that's what that other molecule does, is it says, thank you very much, let me have those electrons. And so the reactant that was oxidized is the agent of reduction, or it's the reduction agent, and vice versa. The reactant that is reduced is going to be the oxidizing agent. And you might be saying, yeah, but those sound like the same thing, like oxidizing agent, potato. It sounds the same, but you can think about it as like the agent of oxidation. That's kind of what goes through my head when I see oxidizing agent. This is the thing that is oxidizing the other thing. Like it's being reduced itself, but it's really good at stealing those electrons away and oxidizing the other compound that it's reacting with. At the most basic level in a redox reaction, you're going to have one species that is reduced, and that's going to be the oxidizing agent. And you have one species that is going to be oxidized, and that is the reducing agent. So if you have to put that on a note card to memorize it, do it. I think it's probably always better to have a conceptual understanding and like be able to figure out what these terms mean on the fly than just like trying to recall what is an oxidizing agent, what is reduction, blah, blah, blah. So understand it, but if you have to put it on a note card, do that. So I'd say the takeaways from this very first part of the podcast, and these are important for, being the first 8 minutes of the podcast, is that oxidation is loss of electrons, reduction is gain of electrons. Remember oil rig, remember the shortcut that oxidation is either increasing the number of bonds you have to oxygen or decreasing the number of bonds you have to hydrogen. Reduction is the opposite of that. And then remember the difference between oxidation and an oxidizing agent, as well as reduction and a reducing agent. All right, so the next thing I want to talk about here is what makes an oxidizing agent good at oxidizing something else, and then what makes a reducing agent good at reducing something else. And more importantly, what makes a molecule better than another at being an oxidizing agent or a reducing agent. And what it comes down to is essentially that the better a molecule is at taking electrons, the better it is at being an oxidizing agent. And then on the other hand, the better the molecule is at giving its electrons away, the better reducing agent it is. And at this point, you might be thinking, okay, that's a great principle, but how do we apply it to real systems? How can I look at a molecule and tell that it really, really wants electrons, How can I tell that it's like Gollum and it just, all it can think about is those electrons? My precious. So what I've done is I broke this down into 3 different factors. The first being electron affinity. And if you remember back to the podcast I did on atomic chemistry, and I talked about periodic trends, you'll know that electron affinity is a periodic trend. It increases as you go from left to right and down to up on the periodic table. So elemental fluorine has the highest electron affinity on the periodic table. And because of that, it is a great oxidizing agent. It really, really, really wants electrons. It wants to just take those electrons from anything. So it's a great oxidizing agent. On the opposite side of the periodic table, you have elemental lithium, which has a very low electron affinity. And therefore, it's a great reducing agent, right? It really wants to give electrons away. And there's another way to think about this that is maybe a little bit easier, and that's that you can think that halogens, which fluorine is a halogen, are really good oxidizing agents because they only have to gain one electron to obtain this very stable state, which is known as this noble gas electron configuration, or where they have a full octet of electrons. And so because of that, they only need one electron to get their full octet. They're a really good oxidizing agent. They can easily, steal that one electron away from different things. On the other side of the periodic table, alkali metals, which lithium is one of, they only need to lose one electron to have that full octet and have the noble gas electron configuration. So it's really easy for them to just lose that one electron, therefore they're a good reducing agent. So you can think about it either way, think about periodic trends, or you can think about full electron octets and how stable things are, once they gain or lose an electron. So electron affinity is that first factor that determines whether something's a good reducing agent or good oxidizing agent. The next thing I want to talk about, and this is the second of the three factors, is that compounds or molecules with large oxidation states tend to be good oxidizing agents. And all I mean by oxidation state or having a large oxidation state is I mean that this molecule has a bunch of oxygen in it. So typically you'll see this as a metal attached to a bunch of oxygen. And this is probably something that you saw in organic chemistry. For instance, chromate, which is CrO4, has a large oxidation state, right? There's 4 oxygen in this one molecule, and it's a really good oxidizing agent. And then you have something like potassium permanganate. Then you have something like potassium permanganate, which is KMnO4, another molecule that has 4 oxygen, which has a large oxidation state, and therefore is a good oxidizing agent. So if you're looking at some kind of organic chemistry reaction and you're adding a metal that's attached to a bunch of oxygen, start thinking about an oxidation reaction that's going to happen. And I'll talk more about that in a sec here. But you see metal, bunch of oxygen attached to it as a reactant. Again, oxidizing. Think something's getting oxidized. So that's the second factor that I've come up with in terms of determining whether something's a good oxidizing agent or a good reducing agent. The third and last factor that I have here is that metal hydrides are typically very good reducing agents. All a metal hydride is what it sounds like. It's a hydrogen attached to a metal. So something like sodium hydride, calcium hydride, and so on. And again, anytime you see a hydrogen attached to a metal and it's a reactant or you're adding it into some organic chemistry reaction, start thinking reducing or reduction. Something's getting reduced in this reaction. And I'll talk about that more in detail in a sec. So those are the 3 factors that I've come up with that can kind of help you and guide you as you try to determine what's a good oxidizing agent, what's a good reducing agent. And really it comes back to that electron affinity. Molecules and atoms that have a high electron affinity tend to be very good oxidizing agents, whereas molecules or atoms that have low electron affinity tend to be better reducing agents. So in organic chemistry, you probably have seen that you can have reduction reactions and you can have oxidation reactions. And typically what you're doing is you're taking some alcohol and producing an aldehyde or producing a carboxylic acid, or you go in the opposite direction. You're taking a carboxylic acid and creating an alcohol from it. And so what I think is important here is to understand the order of the oxidation states of these different oxygen-containing organic compounds. In other words, you need to be able to look at alkanes, alcohols, aldehydes, ketones, carboxylic acids, carbon dioxide, and order those molecules based upon the oxidation states of those central carbons. And the list I just presented was actually ordered in terms of increasing oxidation states. So alkanes are the least oxidized, alcohols are the next most oxidized, then aldehydes and ketones, then carboxylic acid, then carbon dioxide, which is the most oxidized molecule of all of those. And you'll obviously notice that as you get more and more oxidized, all you're doing is adding bonds to oxygen, right? And alcohol has 1 bond to an oxygen, aldehydes and ketones have 2, carboxylic acids have 3, carbon dioxide has 4 because it has 2 double bonds. So it's pretty easy to remember actually, but you just need to know kind of how to step through that ladder, right? You need to know how to go up and down the ladder depending upon whether you're adding a reducing reagent to an alcohol or, whether you're adding an oxidizing agent to carboxylic acid that's going to convert it to carbon dioxide or anything in between. So you need to know how to step up and down that ladder. And in order to do that, you need to know the order of the ladder. With that said, I want to talk about a few different oxidation reduction agents that you may see come up on the MCAT. Hopefully you remember these from organic chemistry, but if not, I'm going over them. And you'll remember that some of these are a bit stronger than others, and some kind of jump up the ladder and skip a step. So I'll talk about that. But hopefully this is a bit of a review for you, and all I'm doing is jogging your memory, and you start remembering these oxidizing reducing agents that you learned during OChem, but was probably a while ago. So let's talk first about the common oxidizing agents that you might see. So the first one I'm going to talk about here is a weak oxidizing agent, and it's the most common weak oxidizing agent. And some textbooks and stuff like to call it mild, like it's a mild oxidizing agent, because I guess this oxidizing agent doesn't like the term weak, so just keep that in mind. And this is called pyrididium chlorochromate, or PCC. And what PCC is going to do is it's going to oxidize an alcohol to an aldehyde. So it's just going to be one step in the ladder. Again, it's a mild oxidizing agent. So that's the most common mild oxidizing agent. In terms of strong oxidizing agents, there's a few that you might see. There is the Jones reagents, which are chromium trioxide and sulfuric acid, which respectively is CrO3 and H2SO4. There is potassium permanganate, which is KMnO4. And then there's chromic acid, which is H2CrO4. And again, it can really be anything that's like a metal attached to a bunch of oxygens. These are just a few of those examples. And in general, strong oxidizing agents are able to convert alcohols all the way to carboxylic acids. You just skip over the step of the ladder that is aldehydes and ketones. And I did briefly want to mention that potassium permanganate, KMnO4, does a special thing where it can actually convert alkenes, which have this carbon-carbon double bond, into glycols, which are just compounds that contain two alcohol groups. And it does that under mild conditions. Basically what happens is that this really strong oxidizing agent, potassium permanganate, breaks the double bond and then gives each of those carbon that was involved in the double bond an alcohol group, or a hydroxy group. Potassium permanganate's kind of like that weird guy at the bar that, you're just standing there with your arms crossed, and all of a sudden he brings you two drinks at once and you got to hold them with both your hands, right? What happens? You have your crossed arms, and that's like a double bond, and then all of a sudden he comes over and now you have two drinks in each hand, right? You got two alcohol groups. So that's potassium permanganate, kind of the creepy guy at the bar, or maybe the nice guy, I don't know. Depends upon, I guess, the situation. But what happens when you take those same reagents and you just heat it even more, you end up actually cleaving the carbon-carbon bond that's left over from that double bond. In other words, under these conditions, you're creating two different molecules, each of which are alcohols. And this is where my metaphor gets a little gory and kind of breaks down. This is where you actually determine that this guy is a completely insane guy, because what he does now is you holding both these two drinks in each of your hands, and he just takes out an axe and just cuts off both of your arms. And now you have two individual alcohol groups. So I think the takeaway, though, is that potassium permanganate is a really powerful oxidizing agent, and it's even powerful enough to take alkenes and convert them to alcohols. So again, strong oxidizing agents are able to convert alcohols to carboxylic acids directly, whereas mild oxidizing agents are only able to convert alcohols to ketones or aldehydes. And the last thing I want to mention here is that there is actually an organic reaction. You probably didn't talk about this in organic chemistry, but there's a reaction that you can take an alkane, which is the lowest level on this oxidation spectrum, and you can actually convert it to carbon dioxide, which is on the highest end of that spectrum. It's at the top, right? That's the most oxidized that carbon can get. And as you maybe guessed, that reaction is called combustion, which is the complete oxidation of an organic compound, an alkane, into both carbon dioxide and water. So just keep that in mind. Combustion is an oxidation reaction, and it's basically the GOAT of oxidation reactions. And finally, it is responsible for explosions. So those are a few oxidizing agents you might see. In terms of reducing agents, there's a few. And remember, this is going the opposite way on the ladder. So instead of adding more bonds to oxygen, you're actually decreasing the number of bonds you have to oxygen. So as with the oxidizing agents, there's some that are mild, there's some that are strong. The mild one to remember is sodium borohydride, which is NaBH4. And what that's going to do is it's going to reduce aldehydes and ketones to alcohols. And then, of course, you're going to have strong reducing reagents, which is going to be something like lithium aluminum hydride, which is LiAlH4. And what that's going to be able to do is it's actually going to be able to reduce a carboxylic acid to an alcohol. But, it will obviously reduce an aldehyde to an alcohol as well. It's not like it's too strong where it turns its nose up at an aldehyde and is like, I don't even want to mess with that. That's below me. It'll reduce an aldehyde as well.
Thanks for checking out the Prospective Doctor MCAT Basics podcast. Sam's doing a killer job taking you through the most important MCAT topics, but what if you need a little extra help? How does a 5, 10, or even 15-point increase in your score sound? Imagine how your chances at admission could increase. Med School Coach's MCAT tutoring can get you there. With the most rigorous selection process of any tutoring company, we see amazing results. We deconstruct each student, find a plan that is going to work, and help execute it. That's why our students add an average 12 points to their score. Completely physician-run and operated, and focusing on nothing but medicine. It's no wonder over 10,000 past students have trusted Med School Coach to get them through the MCAT and into medical school. Check out medschoolcoach.com today and mention code PODCAST for 5% off.
All right, the next thing I want to get into here, and hopefully this is interesting for you, is redox in the context of biological systems. So many biological systems rely on redox reactions. I think probably one of the biggest systems that relies on these redox reactions is the electron transport chain. In the electron transport chain, electrons are transferred to and between carrier molecules. There's a lot of redox going on during these different transfers. And there's two kind of really important electron carriers in the electron transport chain that you'll see come up on the MCAT. And also you'll see this come up on a lot of the metabolism stuff that you may have already learned. That's going to be NAD plus and FAD. And at this point, let me do a quick digression back into metabolism so that you can kind of understand where we're at and what we're talking about. So in oxidative metabolism, our cells are converting glucose to pyruvate in a process that's known as glycolysis. And then this pyruvate is converted to acetyl-CoA by pyruvate dehydrogenase. And then this acetyl-CoA is fed into the citric acid cycle or the Krebs cycle. And the Krebs cycle spits out a bunch of higher energy molecules like GTP as well as electron carrier molecules like 3 NADHs and 1 FADH2. And then what happens is that these electron carriers, which are the NADH and the FADH2, make their way to the electron transport chain, which is like the third part of this oxidative metabolism, sometimes called oxidative phosphorylation. And so the electron transport chain contains 5 transmembrane proteins, which are 4 complexes named aptly complex 1, 2, and 3, and 4. And then the 5th is going to be the ATP synthase. And then what happens is that at complex 1, NADH transfers 2 of its electrons to ubiquinone, which is another electron carrier that is kind of within this electron transport chain. And at that point, you pump 4 hydrogens across the mitochondrial inner membrane. Then at complex 2, kind of simply put, FADH2 transfers 2 electrons to another electron carrier. And at complex 2, there are no hydrogen that are pumped across the mitochondrial membrane. There are at the other 2 complexes though, and what that does is it builds up a concentration gradient of hydrogen, which then can be used to drive the ATP synthase and make ATP. But what I'm most interested in for the sake of this redox podcast is these electron carriers, as I said, NAD plus and FADH. And the first thing you might be thinking about is, wait, but didn't you just call it NADH and FADH2? Well, I did, but really they're pretty much the same thing. One is the reduced form, the other is the oxidized form. So NADH is the reduced form of NAD+, and you can remember that pretty easily, right? Because something is more reduced when it has more hydrogen, so of course NADH is going to be more reduced than NAD+. So you can imagine that NAD+ comes along, it gains 2 electrons in the Krebs cycle, and now it is NADH, and it's carrying those 2 electrons to the electron transport chain. In the same way, FADH2 is going to be the reduced form of FAD, right? Because FAD is floating around, it gains 2 electrons in the Krebs cycle, and then it's going to bring those electrons to the electron transport chain. And I will mention too that electrons can be transferred to NAD plus and FAD in other ways than just the Krebs cycle. So for instance, during beta oxidation of fatty acids, you create NADH, just in the breakdown of that fatty acid, which can then be fed into the electron transport chain, and you're creating more ATP through the breakdown of those fatty acids, which is good. It's important because we get energy from the fats we eat. But I think it's an important point that we don't necessarily rely just on the Krebs cycle for all of our NADH and FADH2 needs. One other thing I think it's important to understand here is that it's not that these molecules just simply give up their electrons. It's not that the NADH knows that its role is to grab the electrons of the Krebs cycle and bring them over and then pass them off to the electron transport chain. It doesn't know that. So what determines whether or not a molecule holds onto electrons versus passes it off to another molecule? What's the determining factor there? The determining factor is how good of a reducing agent a certain molecule is. So for instance, in the electron transport chain, what happens is that each consecutive electron carrier, as this electron is passed up and up and up the electron transport chain, each of these molecules is a better reducing agent than the previous. And in that way, it's able to actually pull those electrons away from whatever carrier is bringing it the electrons. To really see this, you can look at the reduction potentials of each of these electron carriers in the electron transport chain. And all a reduction potential is a measure of how good a certain molecule is at being reduced itself. In other words, the higher the reduction potential or the more positive the reduction potential, the better a molecule is at being reduced, or the better it is at taking electrons from other molecules. And so if you look at the reduction potential of NADH versus ubiquinone, you'll see that NADH has a reduction potential around negative 0.32, whereas ubiquinone has a reduction potential around 0.1. So ubiquinone's able to take those electrons from NADH because its reduction potential is higher. And if you look at the reduction potentials of each of the consecutive electron carriers in the electron transport chain, what you'll see is that with each consecutive carrier, the reduction potential increases. And that's kind of what facilitates the transfer of electrons through the entire electron transport chain, ending in the reduction of oxygen to water. And so what I really want you to imagine is in the electron transport chain, these electron carriers are actually ripping the electrons away from the molecules with lower reduction potentials. They're not very nice molecules. The molecule with the higher reduction potential sees the one with the lower coming in, and it's carrying those electrons, and it's kind of a bully. It says, oh, what you got there? Are those some electrons? I like electrons, and just rips them away, and then laughs and is just on its way. It's gone with the electrons. And the last thing I want to mention here before I go on to the next biological application is I want to mention, and I forgot to say this earlier, that NADH is not the same as NADPH. They have two really different functions. If you want to learn more about NADPH, go listen to the Biomolecules podcast. But don't confuse the two. Don't conflate them. They're not the same. All right, so electron transfer in the electron transport chain is a good example of redox in biological systems. Another is in what are called reactive oxygen species, or ROS. So the National Cancer Institute defines ROS as, quote, a type of unstable molecule that contains oxygen and is easily reacted with other molecules in a cell. And a buildup of reactive oxygen species in cells may cause damage to DNA, RNA, proteins, and may lead to cell death, end quote. Examples of ROS include things like hydrogen peroxide, which is H2O2, superoxide, which is O2 in parentheses minus, and then things like hydroxyl free radicals like OH, then with like a little dot next to it. And as their name suggests, these are very reactive species. They're very reactive oxygen species, in fact. And one thing that kind of gets missed in all this is that these ROSs can sometimes serve as important signaling molecules. And so in other words, reactive oxygen species aren't all bad, right? They do cause bad things for cells, but in some ways we actually need them. And I'll get into exactly what the signals or what the things that ROS can signal. But I think it's important to just understand that these aren't all bad. I guess nothing in biology is probably all good or all bad. And this is an example of that principle. With that said, you might be thinking, okay, why are you talking about reactive oxygen species in a redox podcast? Well, in order to create these reactive oxygen species, we need to move electrons around. And in order to move electrons around, we need to do some redox reactions. And one place where these ROS redox reactions occur is in the mitochondria. For example, superoxide, which is this O2 minus ion, is produced by a 1 electron reduction of O2, which is molecular oxygen. And what happens in the mitochondria is that this superoxide is quickly then converted to hydrogen peroxide and molecular oxygen, and that's done by a mitochondrial enzyme that's called superoxide dismutase. And to me, that's kind of interesting, right? The mitochondria has its own enzyme to deal with these superoxide, very reactive molecules. And essentially, one of the things that this superoxide dismutase enzyme is doing is it is reducing this superoxide to hydrogen peroxide, which is H2O2. So there you go. There's your redox reaction. You're making hydrogen peroxide, which, as we know, is not a safe chemical. It's not a non-reactive chemical. That still is a ROS, or a reactive oxygen species. But it's actually been postulated that hydrogen peroxide serves as an important signaling molecule in mitochondria. So as I said earlier, this is where the signaling role of reactive oxygen species comes in. And an article that I was reading essentially said that an abundance of hydrogen peroxide generated as a byproduct of increased cellular respiration in the mitochondria triggers activation and differentiation of cells. So what that's saying is that when cells increase their respiration rate, i.e. they're producing more and more ATP, they're also producing more of these reactive oxygen species, specifically hydrogen peroxide, and that actually triggers activation and differentiation of those cells. Interesting. Another way that these reactive oxygen species are used for good is in the case of what's known as a respiratory burst. So immune cells have the capability of releasing reactive oxygen species in order to kill pathogens. And what I usually imagine going on is I imagine these immune cells like literally shooting the reactive oxygen species at pathogens as they kind of fly by. So, you have a bacteria and it's kind of whizzing by a cell and the cell's like target locked and it like shoots the reactive oxygen species. And that actually turns out that it's not really what's going on. What really seems to be happening is that macrophages will engulf a pathogen, they'll bring it in, they'll phagocytose it, and then they'll expose the phagosome that contains that pathogen to reactive oxygen species. And I'm not sure if the reactive oxygen species were produced in the mitochondria and then like exported and used against the pathogen. That'd be pretty cool. I'm not sure if that's how it works, but it is interesting that cells can actually use these molecules to kill pathogens. And scientists still aren't exactly sure as to how the reactive oxygen species are killing the pathogens. It's a subject that's still up to debate. But one theory suggests that these ROS participate in redox reactions with important enzymes and other biomolecules in the pathogens. And what they're doing there is they're basically acting as oxidizing agents and oxidizing all these molecules that are within the pathogen, let's say bacteria, and they're taking electrons from them, and that's causing them to be non-functional. So, for instance, let's say that a macrophage released this respiratory burst, and as part of that, it releases some hydrogen peroxide into a bacteria. And what the hydrogen peroxide can do, and it's known to do, is it can actually oxidize cysteine residues in protein and cause the protein to have conformational changes, which then makes it non-functional. So that's just one of the ways that potentially these reactive oxygen species are able to affect the pathogen and kill it during this respiratory burst. So I hope this last part gave you kind of a glimpse into how redox reactions are constantly happening in biology. And I want to make sure you really understand redox at the conceptual level, and hopefully this helped you do that. But, in all, I think really almost the most important takeaway is to remember this oil rig. I think that's hugely important. Remember the difference between oxidation and an oxidizing agent. Remember the kind of shortcut definition of oxidation, which is an atom having more bonds to oxygen or less bonds to hydrogen, and vice versa for reduction. I'd remember that. I think those are kind of the biggest things I've seen that come up on the MCAT. There is some other things that come up on the MCAT in terms of oxidation and reduction, and that's more of the Gen Chem mathematical side of it. And so that's what I'm going to get into next. All right, in the last part of this podcast, I want to go over some of the more mathematical, gen chem concepts that will come up in terms of redox. The first being how to determine the redox state of an atom or of a molecule, and the second being the application of redox in electrochemistry and electrochemical cells. So let's start with the first, which is determining oxidation states. So oxidation states are usually indicated as a plus or a minus followed by a number, where that number is indicating the magnitude of that oxidation state. And what we're talking about at this point is we're talking about the oxidation state of each element in a molecule. So take, for example, glucose, which is C6H12O6. We could be looking at the oxidation state for carbon, the hydrogen, the oxygen, and we'd be assigning numbers to each of those. And some of them would be negative, some of them would be positive, but each individual atom would be assigned an oxidation state. And there are a few rules that govern how to assign oxidation states to different elements. I have 7 rules here for you. If you go look at like Khan Academy's page, I think they have an article on this, and they only have 4 rules. Really, we're all talking about the same thing here. I think theirs are a little bit more simplified. I wanted to be a bit more descriptive. So the first rule is that atoms in their elemental state have an oxidation number of 0. And when I'm talking about an atom in its elemental state, it's just a neutral substance that contains only the atoms of one element. So that's going to be like O2, the oxygen we breathe in the air. There's going to be O3, which is ozone. There's going to be P4, which is 4 phosphates connected to each other. S8, which is 8 sulfurs. Just these compounds that contain all of one atom and they don't have a charge. Those are going to be elemental states. So again, atoms in their elemental state have an oxidation number of 0. The second rule is that the oxidation number of hydrogen, which I might mention oxidation number and oxidation state are the same thing. So the oxidation number of hydrogen is +1 when it's combined with a nonmetal. So examples of that is going to be things like the hydrogen that are in methane, for instance, which is just CH4, or the hydrogen that are in sulfuric acid, H2SO4. So those are going to be hydrogens that are connected to nonmetals. And again, a hydrogen connected to a nonmetal is going to have an oxidation number of +1. So that's rule number 2. Rule number 3 is that the oxidation state of hydrogen is -1 when it is combined with a metal. So something like lithium hydride, which is LiH, the oxidation state of hydrogen is going to be -1 there. Sodium hydride, which is NaH, same thing there. Rule number 4 says that monatomic atoms, which are just atoms by themselves, have an oxidation number equal to their charge. And I like to think about this as if they were in solution. So if I throw sodium chloride into solution, the charge on the chloride atoms is going to just be -1. And so these atoms have an oxidation number that's -1. Rule number 5 says that oxygen usually have an oxidation number of -2, except in peroxide compounds. So like in hydrogen peroxide, H2O2, the oxygen is going to have an oxidation number of -1. Rule number 6 combines a few different rules in a way, but it says that halogens often have an oxidation number of -1, whereas group 1 and group 2 metals have an oxidation number of +1 and +2 respectively. And this rule is very similar to the monatomic atoms rule. I just remember it by thinking about the charge on these atoms if they were to be ions by themselves, right? So sodium, which is a group 1 metal, would have a +1 charge if it were an ion. And so it has a +1 oxidation number, even if it is part of a molecule. So if I have sodium chloride solid, the oxidation number for that solid, for the sodium in that solid, is going to be +1. So in a way, I think about these oxidation numbers similar to charges on ions. I'm always thinking back to, okay, if I had this certain atom as an ion, what would its charge be? Okay, the oxidation number is probably going to be that charge. And, there's different exceptions here and there, but for the most part, when you're looking specifically at halogens in group 1 and 2 metals, you can pretty much follow what their charge would be if they were in solution, and that's going to be equal to their oxidation number. Rule number 7, in my opinion, the most important rule, says that all atoms in an ion or molecule are assigned oxidation numbers so that their sum is equal to the charge of that ion or molecule. In other words, this is kind of the last rule that I use, right? I first go through rules 1 through 6, determine what I can about this molecule or whatever I'm looking at, determine the oxidation states that I can, and then I use this last rule to determine the oxidation state of whatever I don't know. And usually this is going to be like a transition metal. So take, for instance, zinc hydride. So zinc hydride is ZnH2. So I look at it and I say, okay, I know I have hydrogen with a metal, and I know that it's going to have, the hydrogen is going to have an oxidation state of -1. That's rule number 3, I believe. Let me check and see rule number 3. That is, in fact, rule number 3. And so what then I know is that I have 2 hydrogens, so together those hydrogens are going to have an oxidation state, each of -1 that's going to be added to be -2. And I know that because zinc hydride is going to be a neutral molecule, that zinc then has to have an oxidation number of +2 to even out that -2. So then I say, okay, zinc has an oxidation number of +2. And now I know the total oxidation state of all the atoms in this molecule. If you're able to do some practice problems right now, take a look at potassium permanganate and see if you can determine the oxidation state of all the atoms in potassium permanganate. And then also try doing like a complex ion. Those are a little bit trickier because the overall molecule has a charge. But, if you're struggling, really what I recommend is just doing a bunch of different practice problems. Make sure you know the rules, obviously, but I'd say practice is a bit more important. Plus, there's plenty of practice online. If you just Google oxidation number practice problems, there's going to be a shit ton of results. So yeah, there's plenty of practice out there. All right, so the last thing I'm going to talk about in this podcast is the application of redox in electrochemical cells. An electrochemical cell is a device that generates electrical current from a redox reaction. You'll probably remember these from Gen Chem. They're essentially these 2 containers connected by a salt bridge and also like electric wire. On one side, you have the cathode, the other is the anode, and then you get a flow of electrons from one side to the other. And more specifically, electrons flow from the anode, which is negatively charged, to the cathode, which is positively charged. And so similar to oil rig, there is a mnemonic you should definitely memorize for this part, and the mnemonic is REDCAT. So reduction occurs at the cathode, hence REDCAT. It's like the first 3 letters of each word. So that helps you remember that reduction occurs at the cathode, oxidation occurs at the anode. And I think it's important to have a conceptual understanding of what's going on at the cathode and anode beyond that you're having reduction at the cathode and oxidation at the anode. So let's say that we're talking about an electrochemical cell that has zinc on one side, copper on the other side. At the cathode, you have copper 2+ in the solution that the cathode actually sits in. So you could imagine you have a piece of copper metal that's sitting in a solution containing copper 2+ ions. And so what's happening is you're actually reducing this copper 2+ to solid copper. In other words, you have copper 2+ gaining 2 electrons to become copper solid. And in this process, this solid copper actually begins to accumulate on the cathode. So the mass of your cathode is actually going to increase over time as you run this electrochemical cell. On the other hand, at the anode, you have solid zinc that is sitting in a solution of zinc 2+. And so what happens is that this solid zinc is actually oxidized to zinc 2+ as it loses 2 electrons. So what happens over time there is that you actually start to lose mass from the anode because essentially your zinc metal is dissolving into solution. And, I get asked this pretty often. So if you ever get asked how to dissolve a metal, you tell them a electrochemical cell. At least that's what I usually say. So I know you probably have one last question on your mind, and that is what determines which compounds at the cathode and the anode, right? You just said, okay, copper 2+ is at the cathode, zinc is at the anode. You just gave that to us. How did you know that? And so this goes back to reduction potential. And I mentioned that a bit earlier, but reduction potential is the tendency of a compound to gain electrons and get reduced. The higher the reduction potential, the more likely that compound is to be reduced, or the better it is at being reduced, which goes back to how much of a bully that compound or element is in terms of electrons. How much does it want to take electrons from other things? And so you can go look at a list of standard reduction potentials, and they're just these half reactions that are shown, and you'll get them in order of typically decreasing reduction potential. And so you can see that there's a lot of molecules that are really good at being reduced. Fluorine, for instance, F2, very, very good. It's got a really high reduction potential. However, lithium, on the other hand, is not as good. But what it is really good at is being a strong reducing agent. So if you combine fluorine and lithium, you're going to have a really strong electrochemical cell, it might explode in the process. I don't really know, but that would be a hell of an electrochemical cell. And so anyways, where I'm going with this is that if you have two compounds and you know that they're going to make up an electrochemical cell, the compound that's going to be at the cathode, which again is being reduced, right, red cat, then that's going to be the compound that has the higher reduction potential. So, you might be given an actual list and asked, out of two compounds, which is going to be the cathode, which is going to be the anode. All you got to know is the compound at the cathode is going to be the one with the higher reduction potential. And I should mention too that the one caveat here is that if you're talking about an electrolytic cell, so an electrolytic cell is one that requires energy to run. It's not spontaneous. And in that case, it'd be flip-flopped. But just imagine for now, we're talking about galvanic cells or cells that don't require energy to run, right? They just run spontaneously. And this is always true. The compound with the higher reduction potential, cathode. So if you don't leave this podcast with anything else other than red cat and oil rig, honestly, that's not bad. You're going to use those on the MCAT. So I think those are two pretty important concepts. Hopefully you found this podcast helpful. Hopefully you have things to do or you're studying really hard during this time when, schools are shut down or maybe you're not going to work or whatever it may be. But hopefully this podcast helped you. If you liked it a lot, go give us a review on iTunes. Helps us reach more people, as well as I always like seeing them. Thanks for listening.
Thanks for listening to Prospective Doctor's MCAT podcast. If you're a pre-med, you'll want to check out prospectivedoctor.com for tons of free tools, articles, and more podcasts that cover your pre-med life. And if you need help on the MCAT or getting into med school,